This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you one of my most interesting projects, or at least in my opinion one of my most interesting projects. And this will be a continuation of a project that I started some time ago, but now I have some new parts and new stuff, so I can basically continue working on that project. And let's start with this circuit here, because this is the first circuit that I built and assembled for this project series. So this circuit is the original circuit of the TCD1304 linear CCD, and this circuit can be found in the datasheet of this linear CCD. So I just copied that drawing, and then I just made a PCB out of it, and then I assembled the circuit on the PCB, as you can see. And this circuit drives this CCD, and then it allows us to read its output signal as well. And there is nothing too complicated on this specific circuit. There is a hex inverter here, and then there is a transistor, 3 resistors, and 2 capacitors. And this is not at all an optimal alignment or arrangement of the components, of course. Anyone could see that. But it's perfectly enough to learn how to drive this CCD and how to read the signal of the CCD. And then I did not stop with this project. The outcome of this project was that I could show you, you can see the video there, I could show you that I can drive and read the CCD, and for example I can capture the output signal of this thing with an oscilloscope, which was actually on my desk here. And I could manipulate the light being exposed to the surface of the CCD, and with that I can manipulate the output signal, of course. But yeah, I did not stop here, and I built another CCD. I stepped up the game, so you can see that this is a more compact PCB, and it's a black PCB. It also has mounting holes, and there are no parts here. So what is the trick? Well, first of all, this has a microcontroller on the other side. So what I did here actually with this very strong prototype PCB is that I designed the SMD parts there. Here you can see the footprint a bit better, but the SMD parts are actually on the back side. So this is where the CCD comes. The SMD comes on the other side and in between the legs of the CCD. So it's a very compact stuff. And actually this was one of my PCB back in the time that I assembled by hand. So it's a very ugly mess, as you can see, and I even messed up a few things. So I had to get the 3 volts with this cable. But that does not hinder me from working with this board, because the board works very nicely, and it allows me to have this very compact construction and drive and read this CCD with a computer via USB. And I also showed this working concept on one of my videos. You can see that video in the corner. So I can read and drive this CCD. And you can see that these are all very nice PCBs, and they are actually provided by the sponsor of this video, PCBWay. PCBWay is a service provider specialized on PCB manufacturing and PCB assembly, but they also have other services, for example CNC machining or 3D printing. And now it is especially worth it to visit PCBWay because they are celebrating their 8th anniversary, so they have a huge promotion, which means that they have several different kind of free coupons based on your spendings on their website. They have huge discounts on different services, for example PCB prototyping, assembling, and so on. As well as they have discounts on CNC machining and 3D printing related services. And you can try your luck and win valuable products by participating in the lucky draw. So please visit PCBWay.com, check their services, check their products, and check the 8th anniversary promotion and sales, because you can have many different kind of cool stuff. So I hope that you like PCBWay's services and you will use them for your next project. So coming back to my project, then the new thing is basically this part here. And this is a, let's call it optical bench. This is actually a spectrometer. So what we can see here, this is a Czerny-Turner configuration, and what we have here is, I can try to explain it in a visible manner. So here we can connect a optical fiber here, and then the light comes through this part where there is a slit inside this mechanical construction, and then the slit determines the amount of light entering the spectrometer, and then it also kind of determines the resolution, and the light which enters via this slit can also come through lenses, so it doesn't necessarily have to be a optical fiber here, but there can be some arrangement of lenses. And the size of this slit is actually very tiny. I think I cannot even show it in the video. I can see it with my eyes, but yeah, it's very hard to show it with this kind of optics. It's just several hundred micrometers, so it's like a few hair diameter. And then the light goes on this direction, and then it falls on a so-called collimator or collimating mirror. So this mirror here is making parallel waves or parallel rays out of these scattered rays which come from the slit, and then the rays which are now parallel are reflected towards this guy here at my left hand, and this is the grating. So the grating has a certain number of grooves on it, and this specific one has 1,800 grooves per millimeter. So basically there is 1,800 cut on this surface. And it also has another property which is interesting to talk about, is the blaze angle. And then once the light is being diffracted on this grating, then it goes on to this focusing mirror back here. And what this focusing mirror does is that it focuses the dispersed light which is coming from the grating, and then it reflects back in this direction, so towards this opening end. And then this is where we should put our detector. And guess what? This CCD will be the detector. So what I will do in a future video, because this would be like several hours if I would do it in this video, I will measure everything very carefully and print a mounting bracket for this guy, so I can mount it directly here, as you can see. And then that alignment will allow me to detect the scattered light. But then what I will do here is, first of all, I will go back to this grating and talk about a little bit, because this is one of the most critical part of this system, because this actually determines the resolution and the wavelength range of the optical system. And this grating, as I said, it has several thousand or several hundreds of grooves per millimeter. And first of all, it's very interesting how this grating is made. So there can be two types mainly, at least which I know about. One is the ruled one, and the other is the holographic one. And the ruled one is basically that they etch the grooves, so the lines on a substrate, and then they coat this edged surface with a highly reflective material, and then that will be the reflective diffraction grating. But then, yeah, this is a cheap process, but it also can contain a lot of errors. So then the optical quality will not as good as the holographic method. And then how the holographic method is made is that, for example, two laser beams or UV beams are interfering, and this interference pattern is basically exposed on a photoresist coated substrate, and then it leaves behind a certain pattern, and that certain pattern is actually the grooves. And then of course there are some other steps which are done, but these are basically the main things that I want to mention. And this holographic method results in a better resolution. So if you want to have a fancy optics, then of course you go for that. And we have to know that the groove or the grating frequency also determines the wavelength coverage and the spectral resolution. And we have to know that if we have a lower frequency, then the dispersion is less and the wavelength coverage is increased, but the spectral resolution is decreased. So then from this, let's say, principle, you can get an idea how to make your own pattern on this, or how to, for you is more like how to select the optimal piece from a supplier. And yeah, the wavelength coverage is basically how much of the visible or a bit more spectrum we can capture or diffract with this grating. So yeah, that's about it. So light enters here, it goes on the collimating lens, which makes parallel rays. It falls on the grating. The grating, yeah, let's say, splits up the incident beam by diffraction. The diffracted beams go towards the focusing mirror, which is here, and then the focusing mirror reflects the beam towards a detector array, which will be a linear CCD right here. So yeah, what will happen now is that I have already prepared the SMD parts on this board, and I will apply solder paste on one of the boards and put all the parts from this board to the other board, and then I solder it. So I will show you a very nice close-up video of this. And yeah, basically I will assemble one more of this kind of board, because this was a bit, yeah, prototype. You can see the cables. And then I will show you how we can basically calibrate our linear CCD, and then how we can measure random light sources. And I will not show all the measurement and all that kind of stuff, because that's boring and very, very long, but I will show the basic principles. So first, let me put together the circuit, and then I will show you or explain you how I do the measurements. And then I will go to my computer and show you the results and how to interpret those results. So the PCB is completed, and of course when I assembled it I made the same mistake as previously. I should have started with these sockets instead of these two sockets, because then it would have been easier to solder everything, but nevertheless I managed to do it, and I think it's a decent connection. So yeah, this is the previous board, and now this is the new board. So actually I will just use one of my CCD, and then I just mount it in the same way as it is mounted here. So there is a small notch here. I don't know if it's visible. At the tip here, there is a notch, and that should face towards the text where there is written USB. And it's in. Hopefully I did not destroy it. So then, since the text USB is there, then we have the USB port. So it's very obvious how the microcontroller should be aligned. So I just try to find it. And it's in. So I will test this at my computer, and I will make some measurements. So now I have to talk about the measurements, because that's the exciting part, I think. So we have this optical bench, and as I said, the light comes in here, and then the diffracted light comes towards this end. So therefore, I will fix this CCD at an, let's say, arbitrary position, as if it fits inside this optical bench. I will fix it, and then I have these lasers. I actually have three equally, let's say, separated from each other in wavelengths, roughly. So I have a red, which should be 650 nanometers. And then I have a green, which is 532 nanometers wavelength. And then I have a blue one, or sometimes they say UV, but I can still see it, and you can see it there. So it's not UV, but it's just blue. It's 405 nanometers. So now what should happen, and I will try to make this visible in this experiment, is I put a paper here, which is just as a canvas or background. And if I shine the laser in the slit, there should be a spot showing up somewhere. And I turn off the lights just to make it more spectacular. So I have to find the slit, of course. But now there you see the red light, right? So that is the red laser light which went through the three optical elements, or four if we count the slit as an optical element, and then it ends up on the right side here. So then if I decrease the wavelengths, we should see spots towards this direction. So I take the blue, take the green, and then that should show up in the center because it's a lower wavelength. And I try to find the slit, and there we go. So we have the green light there. And then we have the blue light. And surprise, surprise, nothing shows up. And I will tell you why. I put back the lights and I tell you why. So what happens to the blue light? So the problem is that, let's say I put this paper back here. So if you remember the red light, so the highest or largest wavelengths, 650 nanometers, ends up on the right side of this paper somewhere. And then if I decrease the wavelengths, we are going with the peak of the light towards there. So we have red, orange, yellow, and then green, and then blue, and then violet. But the problem with the blue laser is that it gets, let's call this scattering. So it gets scattered so much by this diffraction grating and the other pieces in the optical system that it is just getting scattered out, and it doesn't get, let's say, it doesn't fall on the surface of this paper. So that is a too low wavelength or too high frequency for this specific optical setup. So we cannot go down in 405 nanometers, but we have 2 points. So about the calibration. So why I showed you this laser thing is that we know that the laser is a coherent light source, which means that it has a very specific wavelength when it is operating. So it's not like a light bulb or something that is emitting a mixture of wavelengths, but this is a very, very, very well controlled wavelength. So it has a very narrow distribution in ideal case. So what we can do is that I can put my CCD detector here, physically fix it here, so it has a certain, let's say, coordinate system. And then I shine the red laser through this system, and some of the pixels will be illuminated by the laser. And I know their physical number, like, let's say, pixel 274 is having the peak of this light. So I know that if I read 274 as the peak of the light valley, I will show it what I'm talking about on my computer, then I know that that belongs to the 650 nanometers. And then CCD is still here. I shine my green laser through this, and then that will hit somewhere at the center of this CCD, and that belongs to, let's say, 1784 pixel. That's where the highest intensity of this peak is registered. So then I know these two numbers for the wavelengths, and I know the two numbers for the pixel numbers. So then I can set up a calibration, and basically I can put two lines on a graph, fit a linear slope on this, because two dots determine, or points determine, a slope, and not with a good precision, but now we have to work with these two light sources because I cannot make the third one work. But yeah, so I have these two dots, two pixels here, and based on the linear fitting, if I play around with the formula, I can substitute the peak where I, or pixel where I detect a peak, and based on that pixel I can calculate the corresponding wavelengths. So that's how the calibration will be done. And how I test this is I have 5 LEDs, a yellow one, a green one, a red, a blue, and a white one. And I will fit these LEDs inside this hole. You can see that they fit there, and I will power them up, and I will capture their spectrum. So I will show you on my computer each of these spectrums, or spectra, and based on the calibration which I made using the red and the green lasers, I will try to determine the wavelengths of these guys. So I think that will be the rest of the video, that I'm just showing you basically the results, because it goes quite slowly to do everything, because I have to cover this and I have to fix this somehow here, because this is just a prototype right now. But then if it works, then I will show you the results. So let's go to my computer and I will show you the results of these, let's say, measurements. Okay, so here we are at my computer, and right now you are looking at a software called QTI-Plot. If you are working with scientific stuff and things like that, you might be familiar with Origin, and this is basically the copy of it, or it's a very similar software. However, this can be bought for much cheaper price. And I really like this. I used this for several of my theses when I wrote them, and several of my publications. And you can make very, very nice charts very, very easily. But of course now I'm going to show you ugly charts, because here the purpose only just to demonstrate what I measured. So what you can see right now is the spectrum generated by the red laser. And you should remember that we have 3648 pixels in total. So on the x-axis here we have just the number of pixels, so you can imagine them as bins. So we have 3648 bins, and then the y-axis is the intensity. And remember, if you check the data sheet of this CCD, it works, let's say, inversely. So if you introduce light on a given pixel, then the voltage, the output voltage corresponding to that specific pixel will drop. Therefore, you see like very, very high voltage levels here, because the, let's say, zero brightness or not illuminated pixel equivalent output voltage is around the maximum voltage that the CCD outputs or gets. And then whenever there is an illuminated pixel, then there will be a drop in the output voltage for a given pixel. And you can see this drop here. And this is when I was shining a red laser through the slit, and you can see a very narrow peak. And if I get a bit closer, then this is the magnified image of this same graph. But then we can see the inverse dip here, and we can see the, let's say, distribution much better. And here you should, let's say, take an imaginary photo and imagine that this distribution is roughly let's say 75 pixels or 80 pixels. So then this is the, let's say, coherence of the laser when I was talking about coherence. But that's not the topic here. I just want to show you that what we will do here. So I'm not doing any fitting because here we are just demonstrating stuff, not doing any, let's say, scientific work. But you could fit a nice, let's say, bell curve on this or Gaussian distribution if you want. But all I want here is that roughly determine the position of the peak. And then, let's say, you can imagine from these two, let's say, shoulders, it's roughly 156 or 157, something like that. So this will be our one calibration point. So we say that the wavelength, which is written on the laser, which is 650 nanometer, will be at the 156 or 57 pixel. And then we have a green dot or green peak as well, and that is this guy here. So again, I magnified the graph a little bit, and I'm just only focusing on the peak. So we have the peak around 2486, plus minus 1, 2, 3, whatever. And you can see that again we have a relatively narrow peak. So this is also, yeah, let's say 150, 170 pixels or so. But that doesn't matter. What we see here is we have the green laser, and this is its pixel. So the green laser, if you remember, that is 532 nanometers, and then that belongs to the to this given pixel. So now what we have to do is we note down these numbers. So here I noted down the numbers. So when the peak was at 155, that belongs to the 650 nanometer, and when the peak was at 2485, then that belongs to the 532 nanometers. And we suppose a linear correlation between the pixel number and the wavelength. And then I created this curve here, and this is like the very worst case scenario when you can do a linear fit, because you only have 2 points. So the uncertainty or the error of the curve is basically infinite, or yeah, not very good, because you just have 2 points. Of course you can connect them, but what happens in between or outside these two values, you never know. But now I have 2 lasers which could work with this calibration, so I did it like that. So here you can see on the graph that when we were at, let's say, about 155, then that was the 650 nanometers, so this first line. And then this point is 532 and 2486. And then I just fitted a linear slope on this, so y equals a times x plus b. And then I got the a and the b parameters, so the slope of the curve and the y-intercept. And then what I have to do is, now comes the measurement. So on the right hand side you can see these 4 tables: blue, white, red, yellow and green LED. So then each of them have their own graphs. For example, this guy here. So this is the blue LED, and this is again just the zoomed graph. I will show you the full if you are interested. But then again I did this cheating that I roughly looked at the peak, let's say 3000, and then I noted that down. And here I just only took the pixel value. I don't have the value for the wavelengths. That will come from a calibration equation. this is how the chart looks like. So there is a little bit of background light probably, because I could not isolate the light perfectly. So this is how the chart looks like, and then on the right hand side we have the peak for the blue LED. Then we have a green LED, and then here is the peak around 1720. Here how the whole thing looks like, and then I repeated all of these for the red, for the white and the yellow. So then I have my notes here. So yeah, I noted down where is the peak for the two laser colors, and then I have the parameters from the fitting. This is the equation for the fitting, and then I measured these. So blue LED, green LED, and so on. And I noted down the pixel values for each individual peaks, as you can see. And then what I did, I substituted X as these values in those equations, and then the Y, so the result, gave me the wavelengths. So you can see that the red LED turned out to be 622, the green 570, the blue 504, and the yellow was 577. And this might not tell too much, so let's look at an image. So here I have this image. I took this image from the Hyperphysics website, and you can see the color versus the wavelengths chart. So once again, the red says 622, so that is somewhere here on the borderline of the orange and red color, so that looks fine. And then the green LED is 570, so we are on the borderline of green and yellow, and that's true, I can confirm, because I could see even with my eyes that that green LED is really yellowish and not really green, not like this kind of green here, but more like this kind of green. So even with my eye, uncalibrated eyes, I can tell it. And then blue LED was 504, so that should be somewhere here on the border of the cyan and the blue color. And that is a bit surprising, because then if this calibration is more or less reliable, I should have seen my blue laser, but I could not see it. So yeah, there is a question mark here and there. And then the yellow says 577. That is also here, the yellow. And that is true, of course, because yeah, you can really see that that's a yellow LED, and really the wavelengths fits there. So the conclusion of this study is that we can have this kind of CCD. Of course, this is used for this kind of purpose, but even at my homemade circumstances, I could make kind of a spectrometer. And of course, this is just the first iteration of it, so this will be much, much more better. But what we could see is that I could choose a, let's say, calibration source, for example, a laser, and then select different colors of lasers, use them to determine which wavelengths will be over which pixel. And then based on that, I can have this linear equation. And using the two parameters, B and A, from the equation, then I can identify any peak and say that, okay, this peak belongs to the blue color, or that belongs to the 549 nanometers wavelengths, and so on. And one more thing that I did not show you is the white LED, and I wanted to leave this just for fun. So let's plot it, and now you can see that this is flipped. So this is how the white LED looks like. So here you should see some kind of a similarity between these two, and that is not just a coincidence. So I just also put this chart here and wrote white LED here, And what you can see is that the blue LED has its peak around 3000 pixels, and then the white LED also has a peak close to, let's say, 2500 pixels, so it's a bit more green. But that's what I want to mention here, is that we know that the white light is basically the mixture of all lights possible. And here, that is exactly what we see, is that we can actually identify a little bit dips here and there, because probably those come from the individual components that, let's say, overpower more components. So for example, you cannot see a strong dip around red, but you can see some kind of dip here, which is roughly the yellowish color, and then we go towards the green and the blue color. So where we have this valley here, that suggests that how the white LED is created, or how the white light by the LED is created, is more like mixing together yellow, maybe green and blue color together, and that sort of cheats our eyes, and we see it as a white light. But you can see that this is a kind of a mixture of different lights. And of course, if we have other kind of light sources, like these fluorescent tubes and those kind of things, then we can see much more interesting peaks. Especially if you have a mercury vapor light. I want to get one, but those are stupidly expensive and I cannot really afford them. But they have very, very well determined peaks, and they are actually used for calibrating optical instruments. So that would be a very nice addition to my scientific stuff, but not today, because yeah, it's an expensive stuff, and I don't really trust the shipping as well, because if it breaks, that would be very expensive to replace. But yeah, you can see that we can figure out a lot of things just by measuring the wavelengths of the light. So then how I will continue this project is that I will, for example, improve my PCB. So I will probably make an even smaller PCB just to get closer to the optics with this CCD. And then I will also 3D print a few parts just to make a very, very sealed and nicely assembled enclosure for this optical system. So no stray light can get in and so on. So I will work on that as well. I will also improve the software which captures the data coming from the CCD. So that will be also another step. And then I will try to show you more and more examples where we can use the wavelengths of a certain light and figure out stuff based on the measured wavelengths. So if you want to support my journey and help me, you can go to my Patreon site, link is in the description, and you can support me. So I can buy more stuff, for example, these kind of optical things, and improve the content of these kind of videos. Also, please visit the website of the sponsor of this video, PCBWay, because you can buy, for example, both of those PCBs that I showed you, and then you can recreate these projects that I'm showing you right now. And also don't forget to visit the website, link is in the description, because the website for this video, or web page for this video, will contain these charts and some other interesting things in addition to the things that I'm showing you in the video. So I hope you liked this video, I hope you learned something, and see you in the next video.